Hello, everyone. We're going to talk now about a technique called reduction of order. More specifically, we're going to reduce a second order to a first order differential equation. And presumably, we know better how to deal with first order equations. And these are often not going to be constant coefficients. They're still linear. We're going to still work with linear ones. There is one example in the homeworks, which I'm not going to assign, but you can look it up, where one treats a non-linear one. But we always stick to the linear one. So remember, this for us would mean that it is the form y double prime plus pxy prime plus qx equals qxy equals fx, the forcing function. Sometimes, of course, one writes this slightly differently. If there are denominators, one puts this, we clear the denominator so that there will also be a term here. Let's stick to the standard form. The textbook uses the other form for this. It switches a little bit from form to form. I rather stick to the same thing. Okay, so the technique is the following. It actually works very nicely, but there's one major drawback. Is you need to know already a solution of the homogeneous one. Okay, so we need, for this to work, we need to know a solution, so not all of them, but just a solution of the complementary homogeneous one. Equation, which of course is y double prime plus px y prime plus qx y equals 0. If we know one of those, so let y h of homogeneous, in the textbook they use a different subscript, let y be such a solution, be a solution of this equation. So then we do again variation of parameter. We look at the function y of the form u times y, that's homogeneous one, as we would do before. So this is exactly what we would do if for linear first order, right? We took a homogeneous solution, a general homogeneous, one particular solution, and we multiply it with some parameter, with some function that depends on x, the u, and then we looked for a particular solution. So it's the exact same technique, but there is one little thing that you have to remind yourself of. Whereas in first order, any homogeneous solution is a multiple of a given one, right? If you have one, then you have the other ones are just multiples of it. This is not the case in two linear differential equations of order 2. There you have a fundamental system. There you have two different homogeneous solutions, and every other homogeneous solution is a linear combination. Okay? So we are not saying that we know the fundamental system here. We know both. We only know one. And then we use that one. So that's why it's slightly different. In the next section, which I'm not going to cover too much in detail, we will actually approach it from the other angle, namely looking at both of these, the fundamental system of equations. But of course, then you need to know it. And here you only need to know one single one, which sometimes is easier to do because sometimes you can kind of guess or look or see whether the solution. Now, as a warning or whatever, as a note here is that in this section we will always be given this homogeneous solution. So how we find this homogeneous solution is not at stake here. The question is then, if you have one, how do you find every one? How do you go from one to every? And because there are many, right? We know that there's, and we know how much. It has to depend on two coefficients here. There will be normally two coefficients, right? That's how we know that's the general theory. Well, in fact, we know that a general, so this is a specific homogeneous solution, right? A general homogeneous solution is, as I said, this is a1 times y1 plus a2 y2. We have a fundamental system of equations, and then the general solution would be a particular solution plus a1 y1 plus a2 y2. So I'm putting this in parentheses because that's not what we're going to use. As I said, this is something for the next chapter. We now have just one. So this, for some choice of a's here, we have given one. We don't know we don't know the one y1 and y2. We only know one single one. Okay, so and that's what we're going to do. And what the result of that will be, it's kind of miraculous. It will make it into a first order equation. So which we have better techniques for. So let's do right away an example. There's no point in doing this abstractly. So here's an example: x y double prime minus 2x plus 1 y prime plus x plus 1 y equals x squared. And I want to do let's do initial problem. Y0 equals, give me a sec here, y0 equals 2, and y prime 0 equals 3. I don't think it matters that much. Okay. All right. So first of all, note this is linear. That's the case, but not constant coefficients. So in particular, you should not introduce the characteristic equation here, right? Think about it. What would that be? I mean, okay, for the homogeneous. So let's look at the homogeneous one. So the complementary homogeneous one would be x y double prime minus 2x plus 1 y prime plus x plus 1 y equals 0. If you would try to make it the characteristic equation, you will replace this by t squared, this by t, and this by constant, right? But you would have x's in there. That's not an equation. Equation is supposed a quadratic equation has to have real coefficients, not parameters, not variables. Okay. So this one I'm not selling. So we are told. So this is kind of let me say here. So somebody else, a nice guy. So okay, let me call him a nice guy, right? So a nice guy gave us a solution, and he tells us the solution is EX. So somebody gave us that solution, and we can double check whether it's true or not. Let's not do that. I'll leave that for you to do quickly at home. This is very quick, right? To check that this is correct. Great. So now having this, what we now do. So the technique is now, so the step one really, because that's not a part of the calculation that's given to us, is now to look at u times this function and do the variation of parameters here. So we know what to do now. We have to call y prime, that's u prime ex plus u ex, and y double prime is u double prime ex plus u prime ex plus, now do the derivative of the first, copy the second, plus copy the first, take the derivative of the second. Okay, so we plug this in. In what? In the, we don't work with a homogeneous one, so this is kind of between parentheses again. This is really what we work in. We plug it in right away into this non-homogeneous equation. It could have been a homogeneous one, but you do the non-homogeneous one. You might say, does it make sense to do the homogeneous one because you have a solution? Yeah, we have only one, and that's not enough. So we'll see an example later that you can use this to actually find all of them. Okay, but let's now go to this particular case. In fact, we will also do it here. So let's plug it in. Okay, x times y prime, u double prime ex plus u prime ex plus u prime ex plus u ex minus 2x plus 1 y prime u prime ex plus u ex, and then plus x plus 1 times y, which is u ex, and that is equal to x squared. Now, there is an ex that, at least at the left-hand side, now we are different now, there's nothing that's not on the right-hand side, notice, right? True that this is one of the forms that we have done in the previous section, 5.4, very undetermined coefficients, but this is not linear, this is not constant coefficient, so it doesn't fall under that rubric, okay? That's different. Okay, so we mean what we have is, okay, as I said, we have this ex, so let's take the ex out, and let's now see what we have. Okay, so what we have. We have an x here in front, so we have to be careful here. So these two combine here. Let me already make this a 2u prime here that I don't. So this x multiplies here. So this x u double prime plus 2xu prime plus xu, right? That is this part. Now here, this part, the ex's are out, so we get a minus 2x plus 1 times u prime minus 2x plus 1 u, and then we have here also plus x plus 1 u. All this is equal to x squared. Now I want to isolate perhaps the ex I can bring to the other side with a negative sign. Okay, so let's do that. So we get xu double prime plus 2xu prime plus xu, I'm going to expand this now, minus 2xu prime minus u prime minus 2xu minus 2u plus xu plus u equals x squared e to the minus x. That's what I brought the ex to the other side and gave it a negative exponent. Okay, well, they promised us a first order equation and it's a second order. Professor, you have been lying to us. Let's see. Okay, xu double prime. What happens with the u primes here? We have a 2xu prime that cancels with that, so we have one left, minus u prime. And then we have an xu minus 2xu minus 2xu plus xu, so they cancel. Okay, that cancels. And then we have a, okay, what did I do wrong here? So something is not right because I know what I have to get and I didn't get it. So these cancels, these xu's cancel, but there is still a minus 2u plus u here, right? What did I do wrong? Did I copy it somehow wrong again? Wait, okay, I know what I did wrong, right? I distributed this wrongly here. This is where I made a mistake. Here, in a distributed this, okay, that is minus 2xu, and that is minus u, not minus 2u, okay. One little mistake. Why do they know that? I'll tell you what in a sec. Look, these cancel. And so what is happening here, and it must happen, and it didn't happen, so I knew I was wrong, is you should not have a u term anymore. Rings kind of vaguely a bell, right? Yeah, this not having a u term from the other time. But we will do something else now. So be warned, it's a different thing we're going to do. Okay, so this is equal to x squared e to the minus x. You say, why would we do something else, Professor? We are what we are in the previous case. No, we are not. Why not? This is not constant coefficients, right? And that is really, this little x here screws everything up. What can you do? So, okay, so Professor, no, it's second order, u double prime. Yeah, but there is no u. So let's call u prime z, and then u double prime is z prime. So actually, if I do it in z, we get x u double prime, which is z prime, minus u prime, which is z, equals x squared e minus x. Miraculously, we made it into first order. Now, think a little bit back on a couple of sessions ago when we actually saw this happening. Do you remember when we were talking about mechanics, elementary mechanics, gravitational forces and so on? That was exactly what happening, right? What we got was originally in Newton's law, we have A, which is the acceleration, which is the double derivative. So it was a second order differential equation. But it's also, A is also the derivative of V. And if you think of it as the derivative of V, then it's a first order equation. If only V is, if you don't need to talk about Y, then, and in other words, if there was no Y term in the whole equation, and go look, that never happened except for at the end we had some case. So this is what is going on here. Okay, so we have here a case where we kind of, if you think of y as position, y prime would be velocity, y double prime would be acceleration. So this would be kind of a differential equation about acceleration, but somehow it becomes a differential equation about the derivative of velocity. Okay, so I use z here. Perhaps it would have been better to use v here. Okay, the textbook does z, but let me do v. Perhaps that helps a little bit better. See that it's the same as what we did with velocity. Okay, so this is v here. So okay, I'm gonna replace this. We don't always have to follow the textbook. Huh? I mean, it just names what's in the name, right? Okay, so we have a first order equation. How do we do this now? Okay, step 2. Let's think about first order equations. This is not what we do. We first look at the complementary homogeneous one. Complementary homogeneous. That is x v prime minus v is 0. We know that this always is a separation of variables, and we see it right away, right? So this is x v prime equals v. So bring the v to the one side and the x to the other side by cross multiplying. So get v prime over v is 1 over x. Okay. If you want, dv over v is dx over x. Makes it much clearer what we're going to do. We're going to do ln v equals ln x. What do we do with the constant here? We want to find the general solution, so we're going to keep the constant. Okay. So plus k. I'm going to rename it slightly, because of course we know the next step we have to do is to take the exponentiate, right? So we get v equals to e to the ln x plus k, and so therefore if we split this, it's e to the k times e to ln x, which is just x. So we could write this as c times x, and c is our constant here. Okay, that's the homogeneous solution. What do we do then? Then we say we do this variation of parameters again with this equation, right? Remember what we do then? We do a variation of parameters. I know that's kind of a lot that we're doing here, right? We take the general homogeneous. Remember how did it work? For a particular solution, you're gonna take u, but okay, we have a u already. So, and this u is still in play. So I'm gonna use a w here times v homogeneous, right? So this is the homogeneous equation. So v homogeneous, the general homogeneous solution to this differential equation, right? So we are now dealing, we reduced this is the reduced order, the reduced equation. So in the reduced equation, we have the homogeneous solution, the general homogeneous solution. We now do the variation of parameters. So this w here, normally we called it u before, but this is going to be the parameter. So it depends on x. On x, okay. The variable is still x. Okay, so this is the formula. Again, this is a formula. So I should align my formulas right. So this is the formula. So in our case, I'm gonna drop the p again. So what is this? W times x. I can take c to be 1 here, right? So I just take 1 here. So this is a solution that now I am gonna work with. So we know what to do. V prime is w prime x plus w, product rule, because w depends on x. And now we plug this into the original equation. So we get x times wx plus w minus wx, that's the v, equals x squared e minus x. So what happens? X squared w plus xw minus xw equals x squared e minus x. This cancels. Is this what's supposed to happen? Yes, remember, that's what's supposed to happen. So what we get is w prime is the x squares cancel, e minus x, and so w is e minus minus e to the minus ex and the deriving plus the constant. So again, let's write the constant. So I'm running out of letters here. K is no longer in place, so I use k again. So that is w. That means that v is equal to that thing times x. So it is minus e minus x plus kx. Okay. All right. So we found the general solution here. Okay. I did it slightly different than. I'm sorry. We could have as well done it as before. Take a particular solution. So take k to be 0 here. So sorry. So I could have taken k 0, and then the general solution is a particular solution plus the general solution. So that's the same thing. Also, I should put a c here so to get the same, to make it look the same, right? I can always rename my constants, right? And I'm going to constantly do this. And since I am allowed to, this is a movie, so that I can do things and then change things later on, right? I can erase things, so I'm going to do it that way instead of using different names. Okay, so let me show that I don't want to choose here. Okay, so what do we do next? Are we done? Well, no, we were supposed to be find y, right? What about v? Well, what was that? What was the thing? What was that? Okay, so here's our formula. It's again a formula if you want. It's a very simple formula, but it's a formula. This one. Oh, v was the derivative of u, so we have to do an antiderivative. So v is the derivative of u. Is the derivative of u. So to find u, we have to antiderive this thing. Minus e minus x plus cx. We have to antiderive this. Okay. So what's the derivative of the first one? Minus x e to the minus x dx. I'm going to do this separately. So here, let's do it here on the side here. Write it here. Minus x e to the minus x dx. What kind of integration is that? Isolate. Integration by parts. Isolate. Because we have an algebraic, that will be the u, and an exponential, that will be a dv. So we have, u and v are now totally different u's and v. So this is on the side. I'm going to use and v, redefine u and v inside here, but it won't interfere with my thing at the end. It's just auxiliary variables, right? You have seen this, for those, many of you are computer scientists, you know that you can do this in a subroutine, rename the variables, right? So temporarily reuse variables. Okay, u is minus x. Let's take the minus sign there, and let's take the minus sign with the other guy for perhaps reasons that will become apparent right away. Okay, so once you make this choice, we have to find du, which is just dx, and we have to find v. Now we have to antiderive this thing, and that is e minus x. That's why I said to keep the minus sign there, then you don't have to deal with minuses. So we know that the formula says that this is equal to uv minus integral v du. So uv, that is x, so minus x e to the minus x. No minus sign. Okay, that's the whole point. X e minus x, okay. And now we have to antiderive minus v, so e minus x du, and the antiderivative of this is minus ex, e to the minus x, and minus cancels, so get x, ex plus ex, plus a constant. Well, okay, this is only one part of the thing that we are integrating, so let's do the integration, the full integration, right? Let me do this, erase this here. So we have now found this part, and this is given by here, so that is x ex plus ex. What is the antiderivative of this? Well, c is a constant, don't forget. So we get cx squared plus cox squared plus over 2. And, well, we're integrating, so we have a new constant. Let's call this d. Okay? And, okay, what we have, this is u. And u depends on two constants. We know that is what's supposed to happen. Now, it's not y yet, but we are almost there, right? Because then here, that's our last formula. This is where did u come from, right? Well, it came from here, right? Or that's the formula, right? And so what we get is this. So our solution is x ex plus ex plus cx squared over 2 plus d times e to the minus x, e to the x, I guess e to the x, sorry, double checking here that I, no, where there's something, some e, oh, e minus x, I copied this wrong. I copied here. There's some minus signs here. There are minus signs here, right? Those guys have minus signs. I was so happy that the minus signs were gone that I, at least in front of it, and I erased everything. So times ex. Yeah, that's why I was expecting this to cancel, right? So we have, if you want, if you expand this, you get an x plus 1 plus cx squared over 2ex plus dex. Okay, so this is the general solution. And then step 4, I guess, or this was step 4, the initial conditions. So we said that if x is 0, then y is 1, and what else did I say? Oh, well, 2 and 3, sorry, 2 and 3. So y is 2, oh, okay, I don't want you that. And that is 3. Okay, so just plug in first these two. We get that 2 is equal to 1 plus d. Okay, so these two terms disappear, right? So okay, d is 1. Oops, yeah, do. So d is 1. And now to do derivative, to plug in this condition, I have to take derivative of this top thing, that is derivative of x plus 1, that is n1. Derivative of this guy, okay, derivative of the first term is 2x with the 2 cancels, so cx ex plus copy that term, take derivative of the second, plus dex, sorry, plug in 0. Again, these two guys disappear, so we see that 3 is equal to 1. Wait. Okay, what is, I'm doing something wrong here, right? Okay. So, okay, why am I stopping? Because something is wrong, right? Because look, if I now plug in 0 again, I get a new condition on D, which actually contradicts my previous condition with D, but worse, it doesn't give me C. Why is that? Well, I added this very quickly at the end here, right? And I made a mistake, because these solutions, if you look at the solutions here, they look innocent, right? Because, okay, there's nothing wrong with this function, but this is not a solution when x is 0, because the x, whatever, so the coefficient in front of the y double prime should not vanish, because then all of a sudden it becomes a first order, right? So we cannot plug in x is 0. So these are invalid solution initial conditions. That is a subtlety that I don't want to pay attention to too much. You should never get this kind of thing. But of course, I didn't prepare this particular part, so I should have put in here a 1 here. Anything else would be fine. I just put in a 0 there. So let's we have to redo this here a little bit. So so this is 1, and so this will become different. Well, I shouldn't have erased that one. Let me not erase that one. Okay, so let's plug in 1. So x is 1, right? So we will plug it in here. So this one I have to erase. Then I get okay. I should do one more step, right? Because we all agree that why would you write c over 2 here? It's a constant. We should have renamed the constant. So I'm going to rename them first here. And the way to rename it is just replace C by C, C over 2 by C. And so instead of C's, let me call it A's and B's here. Okay, so now it's a bit easier to work with this. So, okay, so we now have to, let me do the thing over again. Okay, so let's now plug everything in. So if I plug in x is 1 and y is 2, 2 is 1 plus 1 plus a e plus b e, okay? So here we have to erase this part. So we see here that 2 is 1 plus 1, so we cancel, so 0 is equal to a e plus b e, we can cancel out the e, so we see that a plus b is equal to 0. Okay, that's the first condition. And now the second one was, we have to take derivative. Y prime is 1 plus the derivative of the first is 2a x ex plus ax squared ex plus bex. You follow it, right? Now I plug in 1 again. Oh, sorry, y prime, I want a y prime to be equal to 1. I'm sorry, y prime equal to 1. Okay, I can change this, right? Because it was just giving you an example. So 1 equals to 1 plus 2ae plus ae plus b, because fortunately be, fortunately because I cannot plug in x is 0, the exponentials do not disappear. Okay, but again the ones cancel, so that's not so bad. So we get the ones cancel, so we get 0 is equal to 3ae plus be. Again the e's cancel, so we get 3a plus b is 0. Oh, I see now. What is going to happen here? Now let's see. Subtract this from that, so we get the top from the bottom, we get 2a plus 0 equals 0, so we see that a is 0, and then we find that b is 0. So our solution was x plus 1 in this particular initial condition, so perhaps not the best of choice. So okay, so let's discuss very quickly, but it's not so important. What do we get here? We know that this is the general solution to the original differential equation, but the theory tells us that it is of this form, right? The theory tells us this is how it has to look like. It's a particular solution and then a linear combination of a fundamental system of equations, a fundamental system of solutions. And so what we have here, that's that form, right? So this tells me that this guy and this guy form a fundamental system of solutions. But by the way, we knew that Ex was a solution that they gave us to us. That was the nice guy did that for us, right? But we didn't know that x squared Ex is another one homogeneous solution. Now we get that. So we solve a lot by doing this. This method gives us not just from one we get all solutions, including all homogeneous. These ones are the ones of the complementary homogeneous one. This is the general solution. Okay? All right, let's do another example. Where is this? Okay. X squared y double prime plus xy prime minus y equals x squared plus 1. You do again an initial condition. This time the book has done this for us. Y1 is 2 and y prime 1 is 3. Minus 3. Again, we cannot take an initial condition as 0 because that would make this guy disappear. So that's one thing we have to be careful about. If you really want to know why is this excluded, I wrote the standard form here, right? This is, remember, the standard form. If you do this in a standard form, we have to divide by x squared. And so this px would now be undefined at 0. So we would have a differential equation that is actually not defined at 0, in spite of the fact, if you write it this way, it seems that you can plug in 0. And that is why there is no solutions in 0, at the point 0. If you would, well, there's no direction field, so that doesn't make sense. Okay, good. So what do we do? Okay, that tells us again, some nice guy, so a nice guy told us that a solution is x. Not a major revelation, because we could have tried that, but would you think this x would be a solution for the homogeneous one, right? For the homogeneous, that's why I put the h here. So step 1, we're gonna use y is ux. And remember what we do is our formula again. The formula here is we do y is u times the homogeneous. Okay, so u becomes our parameter. So take derivatives. Y prime is u prime x plus u. Okay, y double prime is this is u double prime copy x plus u prime derivative that is 1 plus derivative that is u prime. Okay, so there's actually u double prime x plus 2 u prime. So if I plug everything in, it's x squared u double prime x plus 2 u prime plus x times u prime x plus u minus ux, and that is equal to x squared plus 1. Now we know what has to happen. Can you say what? Can you pause the video if you don't know what I'm talking about, and think a little about it? What has to happen is there should be no u term anymore. Okay, let's see. So if we calculate this is x cubed u double prime plus 2x squared u prime plus an x squared u prime plus an xu minus an ux. That's exactly what I wanted this to cancel. And what I'm now left with is x cubed u double prime plus 2x cubed u prime equals x squared plus 1. So I'm going to put u prime equal to v. Let me box this so that I later see where this comes from. And this becomes therefore x cubed v prime plus 2x cubed v equals x squared plus 1. Okay, so step 2. Now this one we're going to first find the homogeneous solution, right? The complementary, sorry, let me write that, complementary homogeneous. That is x cubed v prime plus 2x cubed v equals 0. That's x cubed v prime equals minus 2x cubed over v. We can divide x cubed. Why can we divide x cubed? Because we don't let x to be 0. We not assuming that there's a solution for x equals 0, so we can divide. So we really get v prime is equal to minus 2v. So that means that dv over v is equal to minus 2 dx, right? Just doing my usual stuff, separating the variables. So this ln v is minus 2 x plus a constant, let's call it k. So if I exponentiate, if v is e to the minus 2x plus k, we've done this so many times, I can go a little bit quicker, and then the e to the k, e to the k, e to the minus 2x, and then e to the k I'm renaming as c. I said I'm going to give myself the liberty to do it this way. Okay, that's the homogeneous one. So that's the first part in step 2, so part 1, right? Part 1 of step 2. Part 2 is to find the particular solution. V particular is a parameter times V homogeneous. That's the technique that we have seen all the way in the beginning. So this is again depending on x. So we V, again I'm going to write V equals W, and this is in this case e to the minus 2x. The c I can take 1 here. So if I take the, what do I have to do? Take derivatives, right? Because I have a differential equation now. This is the differential equation that I have to solve. So I'm going to take the derivative, but locally only once. W prime e minus 2x, the derivative of the first, copy the second, then copy the first, and take the derivative of the second. There's a minus 2 coming out. Let me write that already with minus 2. So minus 2 e to the minus, yeah, right? Okay. We plug that in, we get x cubed w prime e to the minus 2x minus 2w e to the minus 2x plus 2x cubed v, which is just w e to the minus 2x, equals, what was it, x squared plus 1. X squared plus 1. So, what do we have? I don't like my e minus, I have an e minus 2x everywhere. So e minus 2x everywhere, and I'm going to factor this out here, at least on the left hand side. So again, I can do this with my, okay, so this is gone. And then I bring it to the other side, which I do in the next step here. So we will have the right hand side becomes x squared plus 1 e to the, now positive here. And so what we have here is x cubed w prime minus 2 x cubed w plus 2x cubed w. What is this x? Oh, this x was just an exponent that I forgot to erase. Okay. So what we need, we know what has to happen is that this has to cancel, and then we're left with this one, x squared plus 1 e to x. And what we now have is a separation of variables, right? So w prime, or rather an integration problem. So we're going to divide by x cubed, so this will become, sorry. I'm sorry, guys. Something is not right. What did we do wrong here? Okay. Did I think I think I made a mistake here. Oh, I see already. Guys, I made a mistake here in the beginning. All the way back. I'm so sorry. You see, you have to be so careful with this. It's harder, of course, that because I have to do this with on the screen like this and while I'm talking. So here I combine these two terms and I say, okay, that becomes 3x squared. And what did I write? 2x cubed. Silly, stupid me. Okay, so I'm sorry. So all that I said before, I have to redo this. It's not too much, but yeah, well, kind of a lot. Okay, I'm sorry about that. Of course, you can say, how will we figure out this? Yeah, you won't. The only reason that I hesitated was because I saw that what I'm getting is an integral that I don't know how to solve. So there was something wrong with the integral. Okay, so this had to be 3x squared. All right, so this is now our u prime is v, so x cubed v prime plus 3x squared v, because u double prime is v prime, right, equals x squared plus 1. So here we have to do step 2, I guess. We're going to solve this, the homogeneous one, the complementary homogeneous is x cubed v prime plus 3x squared v is 0. So let's bring this is separating variables. X cubed v prime equals minus 3x squared v. So not all the x's disappeared. So what we have is v prime minus 3 over x v. And if separate the variables, dv over v, the v goes to this side, equals minus 3 dx over x. We interderive, we get ln v equals minus 3 times ln x. Okay, we can plus a constant, although in this case we really only need one homogeneous solution, but okay, let's keep doing what we normally do. So we take e to the ln x to the minus 3. Okay, I bring the minus 3 already in the ln because then it will cancel. Okay, and then we do the usual trick with this ek times e to the ln x minus cube. They cancel, so here we get an x to the minus 3. So, and again, renaming this constant as c, we get c over x cubed, writing it with positive exponents in denominator. And, okay, sorry, of course here is v, so here we were exponentiating, right? I shouldn't rush. Okay, so v, so we find that the homogeneous solution is c over x cubed. Okay, so step 3 now is, while solving this first order differential equation, now we do again parameters. What is v? V particular is w times v homogeneous, so this is depends on x. Okay, and so in our case this means v, I'm dropping the p again for particular, w, and the homogeneous I choose x cubed. I choose c to 1. Okay, so this is v. perhaps now it's better to write it with a negative exponent because I need also v prime. V prime is w prime x minus 3 minus 3x squared w. No, sorry. We're taking derivatives, right? So yeah, be careful here. Take derivative. The exponent comes down, okay, and then we subtract one of the derivative. Okay, so that is v prime. So we plug this in now in our equation, in this differential equation that we now try to solve. So this is x cubed w prime and let me write it again now as in the denominator minus 3. No, that's not w prime here, that's a w. I'm sorry, I was so focused on getting the derivative of that thing, yeah, then I wrote a w here. Yeah, minus 3w over x to the fourth. That is this, the first term. The second one is 3 times plus 3x squared w over x cubed, and that is equal to x squared plus 1. Yeah, x squared plus 1. So what we have, we get some cancellations here. Well, we'll expand this. So with w minus 3w over x plus 3w over x equals x squared plus 1. And again, what needs to happen is that these two cancel. Okay, it happened the previous time too. I just started from the wrong equation, but I did everything correctly. I just started from the wrong equation. Now, okay, I'm at the right equation. And okay, it's very nice. W prime is x squared plus 1. So w is just the antiderivative of this thing. That is x cubed over 3 plus x plus a constant. Okay, we keep the constant now because we're gonna go move on. What is w? Where does w come from? Well, w is given by this formula here. So actually, v is that w. Is w over x cubed, so that would be 1/3 plus 1 over x squared plus c over x cubed, and divide this thing by x cubed, right? So that is my v. Am I done? No, because where v comes from? It comes from here. U prime equals v. So this is u prime is 1/3 plus x to the minus 2 plus c x to the minus 3. Why I write it this way? Because I'm going to take the antiderivatives, right? So this is, I have to antiderive this. Let me do this. So this is 1/3x plus, antideriving is add 1 to the exponent divided by the exponent plus c add 1 to the exponent divided by the exponent plus another constant, d. So we get 1/3 x minus 1 over x minus 2c 1 over x squared plus d. Sorry, and again, why should I write minus 2c? I'm gonna write this as a and b here because I don't think I'm gonna change them anymore. Okay, so is that it? No, because where does u come from? U comes from here, here. So we have to multiply this whole thing with x. So y is ux. So that is 1/3 x squared minus 1 plus a over x plus bx. Okay, so now I'm right. Good. That's the general solution. Okay, we have the a and b. It also tells us what the homogeneous solutions would be. This fundamental system for homogeneous solutions. Remember, this is what the a and b give you. You look at the functions in front of a, that is 1 over x, and in front of b, those is x. Now, this night guys told us that x was 1, but he didn't tell us that 1 over x is. We found that. Okay, and this is the general solution. So now the initial condition: if x is 1, then y is 2, and y prime is -3. So when I plug this in here, I get that 2 equals, let's see, in here, of course, 1/3 minus 1 plus a plus b. Okay, so that minus 1 comes to this, it is 3. So the plus 1, that becomes a 3. Sorry, bring this to the other side, that becomes a 3. And then the 1/3, that becomes 8/3 equals a plus b. And then I need to take the derivative of this thing, so y prime is 2/3 x. The derivative of 1 over x is minus a x to the minus 2. Sorry, not if I put it here, x minus 2, let me write it that way. I'm doing the power rule, right? And the derivative, derivative, I'm taking derivatives, right? Am I taking derivatives? Yes, I'm taking derivatives plus b. Okay, I plug in 1 now, I get minus 3 equals 2/3 minus a, because I plug in 1 in there, plus b. Bring the 2/3 to the other side, so it's 9/3 minus 2/3, so it's minus 11/3 is minus a plus b, right? Did I get that right? It's minus 2/3 plus 9, yeah, minus 11/3. Okay, so we have our two equations here. Let me write the other one underneath of it, is a plus b. So a good thing is to add them. So minus 11/3 plus 8/3 is minus 3/3, which is actually negative 1. The a's cancel and we get 2b. So we see that b is minus a half. And once I know that, I know what a is, right? I can plug it in here, for instance. So 8/3 is a minus a half, so that becomes a half here. And so, and if I put this on common denominator, so this would be 3/6 plus 16/6, so 19/6. Double checking that I got this right. Just some number crunching. Yes, okay, I got it right. So the solution is y equals 1 over x this minus plus, but a was 19 over 6 is an x here in the denominator, plus, and that other was minus a half x. Okay. So one last one, a bit quicker, to show you that this, we've seen this, but just to show you that we can now find, even if you only know one homogeneous, we can find a fundamental system of equations. So this is in general now, right? So if we have, so here is an example, x squared y double prime minus 3x y prime plus 3y is 0, so it's homogeneous. And we, again, nice guy, told us that, well, y equals x is a solution. Okay, using that, let's show you that we can now find everything. Okay, step 1, we vary the parameters again. We do u times that homogeneous one, x. So y prime is u primes x plus u, and y double prime is u double prime x plus u prime plus u prime. So this is u double prime x plus 2u prime. We did this before already. We can plug everything in. That is x squared u double prime x plus 2u prime minus 3x u prime x plus u plus 3 times u, and that is equal to 0. So what we get, we have an x cubed u double prime. We have a plus 2 x squared u prime minus 3x squared u prime minus 3x u plus, wait. Oh, why is ux? Sorry, I forgot a capital ux here. Plus 3ux is 0. Why again did I hesitate? Because it has to cancel. Remember, there's supposed to be no u in there. Okay, now we're there. So, okay, combining these things. Okay, professor, be very careful because you're very bad at that. Okay, am I right now? Oh, now I'm right, right? Okay, x cubed u double prime equals 0. I can actually divide by x. Well, let's divide by x cubed. U double prime minus u prime over x is 0, just so that we keep sane by all the different things. Let's keep writing this as v u prime, right? So then so v prime would be u double prime, so this becomes v prime minus v over x is 0. Oh, that's separation of variables, so this v prime is v over x, and if you separate this, then get v, or rather dv over v is dx over x. So if I derive this, I see that ln v, so I think the derivative side is ln x plus a constant, let's call it k. If I take the exponential, then v is equal to e to the ln x plus k, which splits as e to the k times x. and e to the k I rename into a c. Okay, the standard thing that we have always been doing. Okay, so that's the general solution for v. Now we don't need to find it, it's homogeneous, so we're done. So what do we do now? Well, we go back to what v, where did v come from? V came from v came from here. Okay, so v is cx, so this means that u prime is cx. Well, then and the derive, so u is then the derivative of cx dx, that is cx squared over 2 plus a new constant d. And is that it? No, because where did u come from? U came from this equation. So y is x times that guy. So cx cubed over 2 plus dx. And again, we can rename, so this ax cubed plus bx. That's the general solution, homogeneous because it's a homogeneous solution. And again, this tells us that a fundamental system of solutions are x cubed and x. X we knew, that nice guy had told us, x cubed we found now. So if you wonder, how do you know this, that why is it x cubed? Why is this x cubed coming in? Well, you remember we can take any values for these constants. And so how do you get x cubed? Just perhaps to understand where does x cubed come from, well, take a equal to 1 and b equal to 0. That's one valid choice, and that choice gives you x cubed. How do you get x? Well, you take a different choice, right? What's the choice going to take? A equals 0, b equals 1. Okay, that's just what I'm doing here. Okay, so I'm going to assign homeworks on this. Hopefully it's, and the easy part is that they're going to tell you at least one homogeneous solution. Okay.